All right, so we're in part 2 of 10.4. We're going to talk about polar coordinates, and we're going to do derivatives. So what we're doing is we're just applying what we already know about the derivatives of parametric equations. We're considering a polar equation, a parametric equation. Our parameter is essentially theta. So we're considering our parameter theta, and we have a representation in polar coordinates. We have x equals r cosine theta and y equals r sine theta. So theta is our parameter. Now r varies as theta varies. So we're going to write r as a function of theta. Just to make the functional relationship explicit. We're going to write r as f of theta, and using our expression, our formula for the derivative, the slope of a curve represented by parametric equations, the slope dy dx we said was dy d theta over dx d theta. And if we write out, if we're considering r as a function of theta, then the function dy d theta is going to be, we'll have to use the product rule for dy d theta and dx d theta. So if I just write that out explicitly, this turns into f of theta cosine theta plus f prime theta sine theta divided by theta, thank you, divided by minus f of theta sine theta plus f prime of theta cosine. So I'm just making all of the functional relationships explicit here. So y is a function of theta, and r is also a function of theta. So when we take our derivative, we have to use the chain rule. And when we take the derivative of x with respect to theta, we have to use a chain rule. Or I'm sorry, product rule.
So you're saying it's like y equals f of theta times minus theta?
Right, so I could rewrite this, if I rewrite this, y equals f of theta sine theta, x equals f of theta cosine. So we're just saying, we're just writing r as f of theta. R is a function of theta. So that's where this the product rule comes in, because we have to take the derivative of the product of r, which is a function of theta, and the sine or cosine, which is also a function of theta. So it's just all I did was write out explicitly what dy d theta and dx d theta is. So it's not that we have to memorize this formula. It's not that we have to necessarily use it this way. It's just written out explicitly. And I did that for one particular reason that we're going to talk about here in just a second. So this is our slope of the curve represented by parametric equations in polar coordinates. And one thing to remember: the slope is not, because people always make this mistake, slope does not equal dr d theta. So the slope at a particular point is not dr d theta. The slope is dy dx. So we have to keep that in mind. And a couple of conditions: we don't want dx d theta to be 0, So that'll give us an indeterminate form. If dy d theta equals 0 and dx d theta not equal to 0, we have a horizontal tangent. Just like we talked about before. And then the opposite conditions give us a vertical tangent. If dx d theta is 0 and dy d theta is not 0, we get a vertical tangent. Not equals 0. So our conditions are the same as we talked about for parametric equations. We're just using our parameters, theta, just our normal representations in polar coordinates. Now the reason that I wrote this out, that I made this explicit, is because a couple of things happen. If dy d theta and dx d theta are both 0, we get an indeterminate form. So then we have to use some other tools. So let me switch pages. If dx d theta and dy d theta are both 0, our formula gives us an indeterminate form. So then we have to look at, we'll have to figure some other things out. Now if r, which is some function of theta, passes through the pole, when at some particular theta, so we're going to say it passes through the pole when theta equals alpha, some particular theta, and remember at the pole r equals 0 for any theta, but for our graph, if our graph passes through the pole when theta is some particular value, and f prime of alpha is not equal to 0. So dr d theta is not 0 when theta equals alpha. Our formula simplifies we get dy dx equals tangent alpha. Oh, sorry, this should be not. When dr d theta f prime, when f prime does not equal 0, so we're at the pole, but dr d theta is not equal to 0, we get dy dx equals tangent theta. And this tells us, or sorry, tangent alpha. dy dx is tangent alpha. So this tells us that tangent theta equals tangent alpha. Or theta equals alpha. That line, the line theta equals alpha, is the tangent at the pole. So if our graph passes through the pole and f prime is not 0 at that particular point, at that particular value of theta, then the line theta equals alpha is a tangent line at the pole. So what we're saying, just to shorten it up, so if f of alpha equals 0, our radius is 0, and f prime of alpha is not equal 0, the line theta equals alpha is the tangent line at the pole. So that's the reason I wrote out that formula, is because if r equals 0, but f prime is not equal 0, let me go back here. If f of theta, r is 0, I get, and f prime is not equal 0, I end up with dy dx is tangent alpha. The tangent of whatever that particular angle is that gives me an r of 0. So that's why I wrote the formula out this way, so that we could see that the tangent at the pole, if we have r equals 0, and our f prime, the r d theta, is not 0, then the tangent at the pole is given by theta equals alpha, whatever our particular angle is that gives us r equals 0. So that was the main point of writing it out this way. All right, questions on that? So now we have a way to find our tangent lines, our vertical tangents, our horizontal tangents, and we can examine the tangents at the pole if our graph goes through r equals 0. All right, so let's try to do an example here quickly. We don't have a lot of time. So, our example, r equals 2 plus 2 cosine theta for 0 less than or equal to theta less than or equal to 2 pi. We want the slope of the tangent at pi over 6. That equals pi over 6. We want slope of the tangent at the pole. And we want our points of vertical and horizontal tangency. So this particular graph, let me grab a picture. This is a cardioid. So here's my graph. It's very helpful if you're working on these problems to make a graph in your calculator. So there's what we're looking at. When we're doing these kinds of problems, when we are working in polar coordinates, we want to write our equation in parametric form. So we write in parametric form, and then we evaluate, then we find our derivatives. dx d theta and dy d theta, because that's really what everything depends on. So we're going to write our equation in parametric form and then find our derivatives. So, in parametric form, x equals r cosine theta. When I'm using this as my r, so r cosine theta in this case comes out to be 2 cosine theta plus 2 cosine squared theta. And y, I'm using this as my r, y is r sine theta. And that comes out to be 2 sine theta plus 2 sine theta cosine theta. And now we can calculate our derivatives, dy or dx d theta. When I find my derivative, I'm going to do the derivative and simplify everything all together. We get minus 2. Let me write out one other step. I get minus 4 sine theta cosine theta minus 2 sine theta. And because I have these mixed together, it's going to be easier when I work on these derivatives to have everything in terms of one trig function. We have minus 4 sine theta cosine theta equals minus 2 sine 2 theta minus 2 sine theta. It's going to be easier if I have everything represented in terms of sine. So this is a multiple angle identity. So this is going to be my derivative dx d theta. dy d theta equals, when I simplify this out, when I take the derivative of dy d theta, I end up with 2 cosine theta plus 2 times cosine squared theta minus sine squared theta. And I'm going to use an identity here as well. And I get 2 cosine theta plus 2 cosine 2 theta. Just want everything represented in terms of one function. So this is a trig identity, and this is a trig identity as well. So now I have both my derivatives, and I can do my calculations. So my slope is dy d theta over dx d theta. Dy dx is 2 cosine theta plus 2 cosine 2 theta divided by minus 2 sine 2 theta minus 2 sine theta and at pi over 6, I'm just plugging in pi over 6 for theta. Our slope is, if I plug it in and calculate, our slope is -1. So I'm just plugging in pi over 6 here and I get -1. If I look at my graph, at pi over 6, the slope, that makes sense that the slope is about -1 at pi over 6. So it's at this point, often with this type of problem, where people say, okay, the slope is dr d theta, and then plug in theta equals pi over 6 into dr d theta to find the slope. So don't make that mistake. We want the slope of our tangent at the pole. So for part B, at the pole, r equals 0. So I'm just going to use my expression for r. So 2 plus 2 cosine theta equals 0. So r equals 0. And from this I get cosine theta is -1. So theta equals pi. And I need to verify that r prime of pi is not 0. So r prime of pi is 1 minus 2 sine pi equals 1, so it's not equal to 0. So the slope at the pole, theta equals pi is my tangent at the pole. Question? Uh, It would just be minus 2 sine theta. Yes, thank you. And that should be 1, right?
Why don't you use
that's why we have to do this analysis, because it has a cusp. So this does turn out to 0. Yes? Sine of pi is 0, so this is 0. All right. So at the pole, we have an indeterminate form.
So why are you using R prime? Why are you using the already theta there and not like?
So back here we said that if we look back at our equation for our slope, if r is 0, so f of theta is 0, then this term and this term go away, and we have f prime of theta over f prime sine theta over f prime cosine theta. That would be our slope. So if f prime is not equal to 0, then we can find a slope at the pole. So this side of the equation goes away, and we just have f prime sine theta over f prime cosine theta. And if f prime is not 0, f prime is the already theta. If that's not 0, then we can find the slope of the tangent line at the pole. Yes? If it didn't equal 0, then we would say that theta equals pi is a tangent at the pole, and the slope of the tangent would be just tangent of pi.
You wouldn't plug pi back into dy dx. What is dy dx?
To find the slope.
So if you kind of find the slope of the tangent at the pole, then you plug pi back into dy dx.
Yes. So if I go back, dy dx is f prime sine theta over f prime cosine theta, so which is just tangent theta. So the tangent of that angle would be the slope at the pole. Yeah, because this is my expression for dy dx when r equals 0 and f prime is not equal. Okay. All right. And I'm just going to do so we have an indeterminate form at the pole, so we can't find the slope at the pole because r prime is equal to 0. Let's just do the horizontal tangent, and we'll skip the vertical tangent for now because we're running out of time. So the horizontal tangent is when dy d theta equals 0. So cosine theta plus cosine 2 theta equals 0. Cosine 2 theta is 2 cosine squared theta minus 1. So this turns into 2 cosine squared theta plus cosine theta minus 1 equals 0. So I'm solving this. I want to solve this for where this equals 0. This factors to cosine theta minus 1. That's what gives me my horizontal tangent is when dy d theta equals 0. I want everything expressed in terms of cosine theta now. So this is an identity for cosine of 2 theta to represent cosine of 2 theta in terms of cosine theta. And I plug that back in here, and that gives me 2 cosine squared theta plus cosine theta minus 1 equals 0. Factor this. This is cosine theta plus 1. That equals 0. So cosine theta equals 1/2, or cosine theta equals -1. So our points, we get theta equals pi over 3, and 5 pi over 3. This gives me theta equals pi, which is our point at the pole, which we decided already was an indeterminate form. And so our points, when theta is pi over 3 and 5 pi over 3, we get the point 3 pi over 3 and the point 3 5 pi over 3. So those are our points of horizontal tangents. Yes. So if we go back to our graph really quickly, our horizontal tangents would be, this is approximately pi over 3. So we'd have a horizontal tangent there and a horizontal tangent at 5 pi over 3. All right. Sorry that we had to go so quickly. Homework.
It isn't Friday.
All right, there you go. If you are not here tomorrow, make sure you watch the video.
I didn't evaluate the integral on that one. I thought we just had to just write it out.
Okay.